Okay. So the first chapter, so chapter 3 will be covering on a single DTR. So single means that you have a one time point. Okay, one time point. Later you have a multiple time point, right? So, so we'll start with a easy case first, right? Simple case first, and then move on to more complex case later. Okay. So so here's some so we're gonna study introduce some new concept. So one concept is the treatment regime terminology, essentially, right? So understanding the terminology is important. So basically, treatment regime, you can roughly say decision rule. Okay, decision rule based on current history. But at this point, because we are talking about the single DTR, right? You have just the first visit. So first visit, you have no information other than X. So that means your decision rule is a function of X. Okay, and then all you have to do is just choose a treatment option. Suppose you have give a drug A or a drug B, right? And so that is basically an option. So this is the set of the treatment options, and then D is essentially a mapping, right? So mathematically, it's just a mapping from X to an element in script A, set A. Okay. So then you don't have to have a single decision rule, right? You can actually, you could have a multiple rules, right? You have a multiple decision, and you want to find the best decision somehow, right? So then you can think of a class of rules, right? Class of rules. So that is a DX, so decision rules. So basically D is any, I mean, it's a set of all possible rules whose range is in A, right? Okay, so what would be the simplest possible rule? It's just something called the static rule. Okay, static means it doesn't really use any information, just a baseline, right? I mean, naive, just, and that, I mean, that is something. So there is a static regime. Dynamic means we're gonna use information, use history. So the history will increase, right? If you have a multiple visit, then you have more information as times go by. And but anyway, that is a very interesting concept. So we're gonna try. So here's a graphical illustration of the treatment regime. So basically you have suppose you have only two choices, right? Two options. Then you have a X space, right? You can measure, for example, blood sugar, or right? You can use age group, gender, whatever. So use that information to partition, right? Partition the sample space into two parts. So that's one way to conceptualize this decision rule. And also there could be another one, D2, right? So D1 is one particular rule which basically has a cutoff point in this particular line. But actually you can use different line, right? So this is another cutoff point, so that we give a higher, large proportion goes to treatment A, A1, whatever. But that is basically the concept. And now, second concept is the potential outcome with respect to D. Okay, so decision rule. So basically, suppose I'm a doctor, medical doctor. I'm already a doctor, but I'm a medical doctor. So then I can basically, when I give a treatment, right, I can kind of conceptualize what would be the outcome if I choose D1 over D2, right? So then there could be potential outcome conceptually already. So this is a very natural concept, right? So this looks mathematically complicated, but conceptually it's a very natural thing. Suppose I give this, so this is my rule, right? Using this rule, right? Using this rule, I can either give 0 or 1, okay? And then based on my rule, so given the rule, I can obtain, right? I can either obtain y star 1 or y star 0. Or in general, right? If you have a more than 2, then you could write it this way. So remember, this is an indicator function, right? So indicator function, that event is equal to 1 and only 1, right? So the event here is mutually exclusive because we are not going to give 2. You cannot really choose 2 options, right? You just choose 1 and only 1. So then notice that this D actually depends on X, right? Uses X. But what I care about is a rule rather than what would be the X, right? So rigorously it depends on the actual potential outcome should depends on X, but what we are really matter is to investigate on D. D is what we want to control, right? X we cannot control, right? And also so the Y is sometimes used R. So in the reinforcement, some machine learning literature, R could be used instead of Y to denote that it means reward. Okay, but we use R usually to denote the response, right? I mean, so they might so I don't want to use R here because it might confuse you, but the notation is just notation. So I mean the area, different subject matter area uses different notation.
I have two questions. Is D below to be random or just
D is what I'm going to choose.
Right.
So D is not random. That's a good question. Actually, X is random. So I have just given the rule, right? So if X is given, I choose action deterministically, not randomly. Okay, I do not throw a coin to do something like that. No. So it's basically a deterministic function of. So yeah. So the problem, of course, the problem is, we don't observe the we don't observe the so we only well, the problem is the data set we have is this X and A, right? So this is the data, and then but we are more interested in what would be the effect of so the rule here, right? Rule here is more like a D here, right? This line is D. Okay, well, we'll see further. So
then we need to consider the identifiability, right? Because the positivity assumption does not hold.
Yeah, we'll talk about the identifiability, right? Yes. So okay. First of all, I mean, this is random. So potential outcome itself is a random variable. So we cannot really do anything, right? I mean, so we want to do some quantify, and so we define. So limit like tau is what? Tau is this one, right? Why we care about estimating tau? Because we cannot really. Originally, we would be interested in this one, but this is not really what we can observe, right? I mean, so that's why we use expectation to figure out the effect. So we are going to do the same thing. we cannot really evaluate Y star D for C. So we want to evaluate the expectation of Y star D. So the potential outcome with respect to the decision, I mean, treatment regime. Okay, and by the way, so this Y star D is this guy. Right? So it's just definition at this stage. So we have a name. So we call it value. So value is a concept. It's kind of expected reward, right? So you can say that expected reward because this is the expectation of the potential outcome. So anyway, the value is value over so the higher the value, then the better, something like that, right? So we want to choose one. So basically we have two main research questions in this regards. The first one is how to estimate this value of a particular rule, right? Value of the particular treatment regime. That's very important question. But remember that we cannot really experiment, right? We cannot really experiment. We just use the observed data only to figure out, right? And with some minimum assumptions, but under that assumption, we want to estimate this quantity. So that's very interesting question. Why? Because if you can somehow estimate this, then we are in a position to compare, right? To compare which one is better, right? If is value of D1 is greater than value of D2, then we want to choose D1, right? And then what about multiple, right? Then we can actually want to do some optimization. So basically, eventually we want to find the optimal regime. But that it will be next week, second part. Okay. So this is next week. You know, I'm still studying and preparing the lecture. so it will take time, but at least for the first question I can answer. Okay. So now. Okay. So estimation of a value of the. So remember the goal is we are interested in estimating the value of treatment regime, particular treatment regime. So D is known. So remember, D is given, right? We have a rule already, and just we want to evaluate, right? So, and then using the data, okay. The problem is that this A has nothing to do with could be had nothing to do with D, right? Because I'm going to use current, right? I'm going to use this data to impose a rule, right? So this is a kind of history, right? This is essentially the current history. So it doesn't really has any. So D is my decision, right? As a doctor, I will give a prescription, but that's just a current data I have, right? I mean, well, that's not really true. Actually, this is just the data, but I don't. So this A doesn't have to. So let me back up. So this A doesn't have to be obtained from D, because I will actually change several Ds, right? So I will actually choose multiple Ds and compute the value of D for each different D. But how can I use the single data, right? So that's so the problem is basically in addition to this, I will eventually compute the some kind of so I can compute, right? So I can actually, as long as I know the D, as long as I know the mapping, I can actually construct pseudo, right? So outcome, my prescription. And then this could be, so even if the realized A is 1 here, particular, this could be 0, right? So we could, or this could be 1, right? So everything can happen. Anything can happen. Okay. Anyway, that is the goal. And the challenge is that we don't observe, right? We do not observe. Okay. We do not observe the potential outcomes, of course. So we need to use the assumptions, some identifiability assumptions, and the assumptions that we're gonna use are actually we start using the same 3 fundamental assumptions. Okay. Now, next question is basically, remember we are interested in the value. So the value is expectation of potential outcome with respect to under the D. Okay. So this is the key, one of the key result that we're gonna use eventually. So this is what we were interested in computing, right? So remember that identification means what? Means we want to express our target parameter as a function of observed data, right? Observed random variable. So remember, even if this is a parameter, so parameter is a function of potential outcome, right? Missing data. So parameter is actually an expectation of, so function of the latent variable. I mean, count potential outcome, which is this one. But here, there's no, so X is observed, Y is observed, X is observed, A is observed, X is observed. So everything is observed. So basically, idea is you cannot really compute the Y star, but we can at least express the expectation of Y star as some function of the observed random variable that in the data set, right? So this is the, so once you establish this, that means you can use this one to construct. So basically, see, this one is a value. So then we can simply replace the population expectation by sample expectation, right? So if you replace by sample expectation, so expectation is, so big expectation inside. So the whole thing here. So I guess this you can call, we'll use this one as Q function, right? Outcome model, Q function. So you compute the Q function, and then the indicator. So this is computable if you observe the data. Then if you observe X, you know the decision rule, then you can compute dx. So you can essentially, determine which. So this one has, right? I mean, so this is indicator. Anyway, so this relationship basically gives you an estimator. So that is basically the direct result of the this identification result. Okay. So now we're gonna look at this identification proof more carefully. So okay. So first step is easy, right? Because first step is just the definition. So this is the definition of Y star D. First equality. Second equality, you can usually use the conditional expectation, right? The property of conditional expectation. Then once you conditional on X, then the expectation is only applied to Y star A, potential outcome. Okay. So that is the second equality. It's not difficult. Third one, you use NUC, right? So conditional independence. So you use the conditional independence assumption of the conditional independence of Y star given A given X, right? So that is the NUC. So that's the that's this one. Okay. The last one is what? The last one is Sutuba, right? So basically, if you write it as a sum, so okay. Yeah, for now, let's use one. I equal to 1 plus. Okay. Then conditional, but you are conditional on particular choice, right? So that means you only, so other things are 0, other events are 0. So the only thing left will be A equal to A, and this will be 0, and then this will become A. So that means you are, so then this case, this is equal to 1, and so you will have this equality, right? So that actually establishes Tuba. Okay. So that's very useful result, because the value function, which is a function of the potential outcome, eventually is expressed represented in terms of the observed data, so that you can estimate from the sample. So the particular step, so the actual step for establishing estimating this estimator, obtaining this estimator requires some details, right? So for example, when you compute this conditional expectation, right, the conditional expectation, you need to use outcome model. So that is this one. Oops. Okay. And so you can, well, you can use a non-parametric model or whatever, but let's just use parametric model for now. And then this is just a regression essentially, so it should be straightforward. So this second step should be straightforward. You don't need to use weight or anything. It's just a regression. And then so the step is just the compute. Use the sample mean, right? So sample mean is used to compute the population mean, essentially. Okay, so that's basically the regression, outcome regression estimator of value function of D, right? So the subscript Q denotes the outcome model. So later it is sometimes called the Q learning. In the optimal regime literature, but Q learning, obviously the Q learning means that we are using the outcome regression model. Okay, so how do you? Yeah, this one. I mean, if you follow this one, this is natural, but it's what it really means, right? I mean, so here's some. Well, okay. So given the data, so if we can observe the yi star a, I mean, so I guess here's the idea. So the idea is this guy is an expectation of the y star potential outcome of a, which is expectation of the summation a subscript a, and then star. So y star d is actually derived from the indicator of the d x equal to a. So okay. Yeah. So my point is that if you this is a missing data, right? This is a potential outcome missing data. So, but if you know, if you can if you can estimate it, then you can just use sample mean, right? So that's why I use a subscript n to denote the sample mean, naive sample mean estimator. But but now that this is not observed, right? So this is missing. So then one approach would be that we can use imputation, right? We can use imputation basically. So this is basically a prediction, right? Imputation or prediction. That's it. Yeah. So that is basically this idea for this this estimator.
So
Yeah.
So Q-learning actually does not require the productivity assumption, right?
Well, that is the same story. I mean, if you remember, so that's exactly the same question you would get for establishing two. So this is potential outcome with respect to A. Okay. So this is actually exactly the same version, right? I mean, what I showed, remember, what I just showed is the left side is this one. The right side is what? And then indicator, right? So, okay. So there's actually exactly the same structure. Okay. So this basically, see, this result is the identification result for estimating tau. Right? For estimating tau, we use this one. Right? So this is just the tau is just the expectation of y star 1 minus expectation of y star 0. That is the estimating. So to estimate tau, we need to establish this identification condition. For estimating value of d, right? We have just established this equality. And when we show this equation 2, we did need this kind of condition. So basically, so Sutuba and NUC, Sutuba and NUC only shows the equality inside the outer expectation. Okay, so using I guess this is given. Okay, let me. That's actually quite important and good question. So I will maybe emphasize it a little bit. So Sutuba plus NUC will only prove y given x a equal to a is equal to y star a given x. And now plus we need positivity, then we can say that this expectation and this expectation are equal. Does that make sense? That answers. Only if they have the same support. So that is the proof here. So this one. So the expectation. So these two expectations are equal. Outer expectation equal only when they have the same support. So basically this, yeah, right. That is actually the proof for showing our result here. I mean, here is actually the same. So positivity is somehow used in evaluating the outer expectation. Yeah, that is quite tricky. Yeah. Okay.
Dr. Kim, can you hear me?
Of course, this imputation prediction estimator, right? Prediction method assumes that requires that the outcome regression model is correctly specified. So interestingly, so the lecture note here in this today has an exactly parallel structure with the lecture note last week. Okay.
Can you hear me?
Sorry, I cannot. I didn't. Yeah.
Can you hear me now?
I can hear now. Yes.
Okay. I was just wondering how you would do variance estimation for these estimators.
Well, that's you can, okay, that you can use linearization. So I didn't. Okay. Well, that's a good question. That's okay. Let me. So sure. I mean, this is, yeah, somehow I have problems. So basically your estimator here is the same thing. So the same question is you're actually asking your tau hat. Sorry. Your tau hat depends on beta hat. So that is estimated noises parameter. Remember, that's exactly the same structure that I covered in my class, missing data class. So remember, how do you estimate the variance of this kind of estimator? So I think I used this kind of notation in the class, right? So how do you estimate the variance of this imputation prediction estimator? Well, you can use Taylor expansion, right? And so basically you need one more equation. So you basically have a one. You need the equation for, I mean, estimated equation for beta, and then you apply Taylor expansion. So you can check the, I don't know, does it answers your question, Caleb?
Yes, no, that makes sense. I figured it was linearization. I just wanted.
Yeah, right.
Curious.
Right. You can either linearization, or you can do also bootstrap, jackknife. So either way, the whole idea is the beta hat has contributes the uncertainty of your final estimator. So you need to utilize that uncertainty, right, in the noises parameter. And if the dimension of beta is finite, then you can easily apply the standard Taylor expansion. That's no problem. If the dimension increase, then it's a little bit more tricky, right? Okay. Good. So I'm gonna move on. So what I was going to say is that, remember the lecture note chapter 2, right? So I have a chapter 2 part 1. So exactly the same structure. So remember, so we defined tau, what tau is. Now we define what VD is. So that is a parameter. You have an outcome regression estimator. And then now you have an IPW estimator for tau, right? And now you will have a AIPW estimator for tau, and then find the optimal one, right? So that's basically the summary of chapter 2, right? And now we are going to do the same thing, exactly the same thing. So we're going to have an outcome regression estimator, which is an imputation estimator. And then we'll study IPW estimator, and then we'll have an AIPW estimator. So that's basically learning, right? I mean, estimate the parameter. So the only difference is that the parameter are different. So tau is more direct, while VD is more derived. It's a still. So direct in the sense that in tau, you compute the A, expectation A, while in V value, you compute the expectation of D. And D, so because Y star, D is derived from Y star A indicator, right? So it's a derived, not, so you define A star, and then you have from the A star, you define your parameter expectation and develop the estimator, right? And then you have a basically parallel. So one Hilbert space, another Hilbert space. So you have a exactly parallel corresponding concept in terms of D, and then do the same thing. Okay. So this is the basically the main subject in today's class. Okay. So then, but the imputation, I mean, outcome regression approach is relatively straightforward. But the IPW is a little bit more tricky. So it took me some time to figure out what's going on. But now I'm quite comfortable. So anyway, yeah.
Can we move to the slides with the assumptions, like the identification assumptions?
Okay. Right here or this way.
Yeah, yes. So the philosophy here is that we have a data set.
Right.
And based on this data set, we want to choose the optimal treatment.
Eventually,
Yeah.
right.
This data set is a kind of random, has some randomness there.
Right.
Otherwise, if we just we kind of unaesthetical, right? So for each patient, we want to use the best treatment we can.
Right.
But we have to have a more randomized data set so that we can do causal inference.
Okay.
Yeah. So if we think about sequentially, right? So we cannot say that at time one, so we get optimal treatment. And then based on the outcome of this treatment, and then we decide on time 2.
Right.
So we have to base on like a difference, like randomized sample
Okay.
that satisfy those 3 conditions. Because if you like use the optimal treatment, it will not, I think it will not satisfy the unconfounded assumption. Yeah, because the A is
I
used to get the best potential outcome,
Okay.
right? So it's not independent of the potential outcome.
A will be chosen to as a function of X. As a function of X, not, we don't observe Y. I mean,
Right, but the goal is to optimize, right? So
Right.
the potential outcome, right? So, and also it will not satisfy the positivity assumption, right? So because if you base on the optimal like treatment regime, that's a decision given X is basically fixed.
so I'm not going to. So we are not really going to give a decision on this observed data.
Right.
So this is kind of a history data, right?
Right, so
And
yeah,
I now have a new patient, right? I now have a new patient. So and all I have is I guess X
right,
for that patient.
right.
Right.
So it's kind of, we need to have more randomized, like some sacrifice
Okay.
for certain group of
Okay.
patients to give us data, and then
see.
we can try to get the optimal
Okay.
ones for the followers.
You are thinking too too ahead. Well, okay, I see. It's in right, but I don't fully, ready to answer with confidence. So okay. Now IPW. So basically I just covered this one, right? So we covered this. I just covered this. So now I'm going to talk about this. So since the problem is essentially a missing data problem, we can also apply the IPW estimation method. Sure, but how, right? So note that we already observe XI, the realized treatment, and we can obtain DX for a given regime, right? So that means I can compute DX, and I can compare with AI and see whether this matches or not. Okay. So that actually gives a indicator function. So this is observed data. This is constructed from my decision rule. Okay. So I can basically, so this is actually original. So this is original data, and this is a kind of derived data. That is the derived. So you derive it using because you know the mapping. So given the mapping, you can compute. Then the outcome is either 0 or 1. If A is 0 or 1, outcome is also, this DX is also 0 or 1. So I can actually see how many of them are consistent to each other. Okay. So that actually, we can treat this event as an indicator function. Okay. and then let's investigate the nature of this event. So this nature of this event is that AI is equal to, so this is small a is just one of the element, right? It's nothing random. But this A is random, capital A is random, X is random. So in order for this equal to 1, we have to have these two have the same value. It doesn't matter which value, right? As long as it is equal to one of the value, then basically, so this is the right one. After that, this is really interesting observation. So basically, the idea is, okay, I create the delta, and what I want is the divide by the probability of delta, right? The propensity. But rather than modeling propensity directly for delta, I can derive. Wow. So that's why I use the subscript D to emphasize that it's actually a good coincidence, right? Derive, and also I use D. So anyway, so using, so this is basically what? This is the delta I equal to 1. So this event has a probability, and then conditional on X, it's nothing random. Conditional X is not random, it's fixed. The only thing random is this guy. And A is random variable, right? With the propensity pi. So I use a kind of a observable notation to A pi AX, because we can think of the multiple outcomes, right? A's. But so basically this is I think is a really interesting idea. So basically the propensity for delta equal to 1 is derived. It's not modeled. You are not really modeling from scratch. We use the model for pi A to use it, right? Derived from PS model for A, basically. So that you're now in a position to construct a nice propensity score estimator where the numerator is a delta D. So you can change D, right? You can conceptualize different D and then create this derived variable, right? Derived variable. I mean, derived treatment. I mean, under that treatment regime, and compare with what you observe, and so that you can do some kind of estimation. So that, okay. So that's basically quite an interesting idea, I think. So then. Okay, so here's a justification. The first thing you should notice is that these two, so delta, yeah, so concept, we introduced a lot of new concepts, so it's a little bit confusing, but anyway, we should do it one by one anyway, right? So so delta D is by definition the indicator of this event, and Y is indicator. So Y is observed Y. So this is a linear combination of the counterfactual outcome, and then these two, right? That means what? That means you can actually, so for these to be, so if this is 0, then we don't care, right? So basically we only care about the situation where, so these two are equal to 1. So then basically this event is equivalent to this event, right? So then once you write this way, this guy is a Y star D. Okay. So once you do that, then you can basically, so first equality basically uses this result, right? After that, things are relatively straightforward. So then you just use the same technique to showing, to identifying the propensity score IPW estimator. So conditional on Y star this is a fixed, so the only thing random is this guy, and this guy is a pi d, so then you basically have a cancellation. Okay. So, okay. So the propensity score, again, propensity score function for delta D, which is this one, is derived from the propensity score function for A, which is the pi A, right? So basically this is this event occurs only one, right? One. So it's just a kind of a mapping. We are not really, it's not really doing the summation in some sense, right? You just choose corresponding event. But mathematically, this is probably the best way we can do anyway. And so then how to estimate pi d? Well, you can use the model, right, for A, and then this is basically the using the, this is the we can observe A, we observe A from the data, observe X, so we can use a multinomial logistic regression model to, so this is the log likelihood function for the logistic whatever the event, right? So it should be doable. Okay, now, so we basically have a outcome regression, right? Q method and IPW method. So now combine augmented IPW method. So that is basically what we want to do here. Okay. So very natural. The only thing is parameter, right? And also we can remember we can change D for multiple. We can use multiple D, and then we can compute multiple estimators, right? So for each D from D, and so we can actually compare, right?
So, Jay,
Yeah.
First propose this is about Susan, right?
I think Susan Murphy,
Yeah.
right? I think, yeah,
The background, right?
yeah. So it's very ingenious, right? I mean, and also James Robinson made a big contribution. But anyway, yeah.
So James Yu is also working this.
Yeah. So we'll see his work next week. He's every week. But anyway, so this is very interesting idea, right? I mean, and also that actually is potentially very useful because it's talking about how to maximize the reward, right? So it's really relevant to our real problems, right? How to maximize the target, marketing, whatever. So this seems to be very useful for making money. Okay. Now, so now how to so what is the, so this is exactly the same problem, right? This is exactly the same problem. So we are probably know the answer already, but let's just be confirm. So the answer is this. So optimal estimator is nothing but the conditional expectation of the this guy given X. But the tricky part is that here's a delta D already. So what I'm going to use is this property. So delta dy is equal to delta d y star d, so that we can actually change it to counterfactual outcome, so that we can obtain this result. Okay, that's it. And then how to compute it eventually is just doing the same argument, right? You can compute the conditional expectation to obtain this. So basically you can use outcome regression model to get best augmentation, right? A function, and then plug in, then it becomes a doubly robust, same doubly robust estimation. So that's basically the whole message. I should prove. Okay. Well, I kind of explained, but let me just since we have time, so AIPW can be written as So delta I D given pi d xi y I star d now. So, well, let's do one by one. yi minus yeah, and also it will be very, very interesting from next week because so many new things and so many interesting techniques. So this is basically the class, right? This is so far, this is just class. Now, what I'm going to do is we just first compute, write it. Remember, we allow to use it, express this one. And then now we conditional on x and y star. We can take the condition expectation with respect to delta. Then we obtain the variance of the 1 over n. I guess we can do something like that. Plus this variance of so what I should okay. So let's basically expectation variance of the conditional expectation of the with respect to delta plus, so that's what I'm going to do, variance of something like that.
So you want to calculate the variance of that estimate, right? So AIT W.
So the whole thing, I mean, here this is the whole thing.
Right, you want to calculate the variance.
Right. And then the variance point is that if you take the expectation with respect to delta, you have a cancellation. Cancellation, this one 0. So you end up obtaining something that has nothing to do with the delta, right? So that is yi star d plus the conditional variance is 1 over n, something like expectation of the something pi d. So this is d pi d over 1 minus 1, and then conditional variance. So that you have a y star d minus l x square. I should, so let me, so this is kind of same thing, but basically, let me write it again to be more rigorous. So y star t minus l x square. Okay, question? Okay, so now what usual technique? So this is what usual technique is what, which, so as a function of x, right? How to minimize the, what is the one that minimize the this term, square term? Conditional expectation, right? So optimal one is a conditional expectation of the first guy given x. Okay, so that's basically the main mess, because this is given x, right? This is a function of x. So conditional on x, the only random is this one. So then you can essentially obtain the optimal solution. That is week 7, I guess week 7 lecture note. You can check. Yeah. Example, week 7 example 1. Same structure. So that's all. So basically this is a same thing, right? Locally efficient and doubly robust. And you can, there's some literature. So that's all for the value estimation for today. And next week we'll study, we'll discuss about the finding optimal the optimal, right? Optimal regime, how to find the optimal regime. So that is the topic.
So what if, so I have historical data,
Okay.
right? I have historical data, I have X, I have Y. But then we discovered a new covariance, which could be quite predictable for the response. And then we want to use this new covariance
Okay.
to choose the optimal D.
Okay.
But this new covariance is like not related to the response mechanism, not response to A. So does this also, because the thing like all the derivation is based on the X and A kind of so the covariance for the D and the covariance for the response are the same, right?
Yeah, I don't know. But yeah, so this, you can see that all the literature is started from 2000 or after. So this is a really relatively new area of research. So I'm sure there's a lot of practical situations that's not really investigated in the literature. So there must be a lot of problems to solve. But yeah, so anyway, I hope that you guys found it interesting and helpful.